And question 2, guys, let's do this. So here we're focusing on bases, modular arithmetic, and trigonometry. Well, not really trigonometry, it's more like triangle rules. So in this series, you're just going to be solving every single one of these problems. It might take a while, but it won't be too bad. So stay with us and we're going to go through all of them very shortly. So let's begin. Okay, let's do the very first one. So here we need to express the decimal number 473 in base 10, that's a decimal number by the way, in base 2. So firstly, base 10, what does it mean? This is actually the standard 0 to 9 format that we use in everyday life. And the key idea is to convert this into the binary 0-1 format. Now I use a really cool trick. I firstly just take the digit, the 473, and simply just subtract it, divide it continuously by 2. That's it. So all we need to do is just draw a line here and just keep on dividing really. So this is going to be the quotient and the remainder. And the key objective is to obtain the remainders because they're going to be in zeros and ones. So let's have a go. So firstly, input the number 473 and divide it by 2. And always convert to decimal or mixed fractions. And you should get 200 and, well, let's do this step here. Let's start with the number. We should get 473 and we should get a quotient of 236 with one remainder. In your calculator, it probably looks something like this or this. The key idea is to use the first one. This indicates that we're going to have a quotient of 236 with a single remainder. And now we just rinse and repeat. So now we put 236 here, divide this by 2, and we should get 118. And notice how it's just a whole number, so there's no remainders. Put this back here again, divide this by 2, should get 59. And just keep going. And again, no remainders here. Divide 59 by 2. And now we're going to get 29. So 59, we're going to get 29 and a single remainder. And just keep going really. So I haven't got spaces, so I'm going to go down again. So let's start from here. So now we start from 29, divide this by 2. You should get 14. With a single remainder, put 14 here, divided by 2, you get 7, no remainder. Divide 7 by 2, you get 3, 1 remainder. Divide 3 by 2, you get 1 remainder. And finally, let's do it one more table here. Dividing 1 by 2, you should get nothing and 1 remainder. And that's it. Now all we do is just chain these binary numbers together. So it seems like quite long, but that's really it. So we start from the last number, so we start from here. So 1, 1, 1, 0, 1, and finally 1, 0, 0, 1. So we go from back to front. This means that the solution is going to be from back to front in terms of remainders only. First, it's going to be 1, and then it's going to be 1, 1, 0, 1. So 1, 1, 0, 1, and then from here 1, 0, 0, 1. So 1, 0, 0, 1, and that's it, all to base 2, and we're done for this one. Okay, part 2 of question A. We need to express the binary number here, so that's 110011.101 in base 2, which is binary, as the original 0 to 9 decimal number. So very easy procedure. I find this one far easier than the previous example, because in this case, all we have to do is simply write all of these digits out in the same way. So I'll do like this, and literally put them in terms of powers of 2. So all we have to do is start from the decimal point here, and this first digit here would be the unit. So this is the same as saying 2 to the power 0, because that's the same as 1, which is the unit. The next digit we just say 2 to the power 1, 0 is attached to 2 to the power 2, and so on. This is literally the position. If you multiply these, if you open these 2's out, or actually solve it, you'll realize that you get 1, 2, 4, and so on. And that's the exact identical value of the position we're in right now. So keep on going. If you go backwards from 0, you're going to get the negative power. So it'll be 2 to the negative 1, negative 2, and negative 3. Now, why do we do this? To convert it back to its original decimal number, all you have to do is simply find the sum product. That is, you just multiply and add. So for example, the way we solve this now, we can convert the number as, firstly, 2 to the power 5 times 1, which is just 2 to the power 5, plus 2 to the power 4 times 1, which is 2 to the power 4. And notice the next two, they both multiply against 0, so that cancels out. So we ignore that. So then we just add the ones that has a 1 attached. So it'll be 2 to the power 1 plus 2 to the power 0 plus 2 to the power negative 1 plus 2 to the power negative 3. And that's it. And when you input that all in the calculator, which I'm going to do right now, so bear with me guys, you should get a nice result. So yeah, go ahead. Put this in the calculator and see what we both get. So we get 2. So just be very careful how you write this, okay? It's actually a very easy problem, but just gotta be careful. But anyway, I got a total result of 51.625. See if you guys get the same thing. And that's it. That's literally how you convert any binary number over here into a decimal number. Straightforward, yeah? Okay, check this out, guys. So part 3. Now we need to express the decimal number 812.25 in base 10 as firstly a binary number and then a hexadecimal number. So just recalling, a binary number are 2-digit numbers taking form of zeros and ones, whilst hexadecimal is a 16-digit number taking values from 0, 1, 2 all the way to 9, and then after 9 we don't say 10, 11, 12, we use the alphabet layer. So we start from A, then we go B, C, D. So the way it works, it goes to 16. So A can represent the 10th digit, so 10, 11, 12, 13. And imagine this as 14, 15, and 15. And that's it. And this represents 16 digits, yeah? Remember, 0 is a digit too, so that's the first, second, third, and so on. So 9, 10, 11, 12, 13, 14, 15. So this is what we use to represent our figures. So let's do the first one first. Let's express the decimal number as a binary. Now, the way this works, we need to work with firstly the whole number part, and then next we work with the fractional part, the 0.25. So let's do this in steps. So working with the whole number first, so let's start with 812. Doing the same method, we need to divide and go, okay? And find the remainders. So dividing 812 by 2, you should get 406 with no remainder. So we can make this in the table again if you like. And then you pull the number down, divide this by 2, you get 203 with no remainder. And then once again, dividing that by 2, you should get 101.5, or in this case, if you get in your calculator, you should get a result like this or like that. Again, use the mixed fraction and the remainder is 1. Now put this number back, so 101 divided by 2. Always do this in your calculator to be safe, and you get 50.5. So 50 with 1 remainder, put 50 there. Half of 50 is 25, no remainder. Half of 25 is 12.5, so 12 with a single remainder. 12 becomes 6, no remainder. 6 becomes 3, no remainder. And just continue on this side. Yeah, let me change the color pen. So on 3. Half of 3 is 1, remainder 1. Half of 1 is 0, remainder 1. And that's it. And like the previous one, we start backwards. So we start from the very last digit and work our way upwards. So we start from here, going up, all the way back to the center. That's it. So we're going to have basically a binary digit of a solution being 1, 1, 0, 0, 1, 0, 1, 1, 0, 0. So now we've done the first part. Now we need to work out what the decimal bit is. So the digits over here. To do this, we need to consider 25, and instead of dividing by 2, we're going to start multiplying by 2. So let's just pull out the 0.25 here for a second. Okay, the first thing you want to do here is multiply this by 2. And what do we get? We get 0.5. And notice how we only take the whole number part, so we just take the 0. Just like this one, you have a remainder of zeros and ones. We're just going to take the whole part, the zeros here, until we finally get a whole number. So now let's take 0.5 across, multiply that by 2 again, and you should get 1. And now we stop. Why? Because we finally have a whole number. And that's it. And this would be our result. And unlike the previous one, this one we take it downwards. Because if you think about it, if you continue to go up, you're going to land towards the decimal number. So this will cycle into the decimals. So the final result will be the same one and 0, 1. Done. Okay, so I've cleaned the page and now let's look at hexadecimal. So same thing applies. So firstly take the 812, so pull it on the side and draw your dotted line. And instead of dividing by 2, like the binary one, we're going to divide this by 16. Okay, that's the difference. Now, one thing to note, if you're using like a Casio calculator, your life would be easy because you can convert your final result as a mixed fraction, and that would be very helpful. So what we're going to do, we're going to write the answer as a mixed fraction here, and then take the quotient remainder step by step, yeah? So it will help you with your calculations. So in your calculator, 812 divided by 16, and then convert into a mixed fraction, you should get exactly 50 and 3/4. Now, the whole point of this is that we want a remainder in terms of 16, so it has to be a fraction over 16. So we can instantly look at this and say 50 and 3/4. If we multiply the 3/4 by 4 up and down to raise it to 16, we should get 12 over 16. And this means we're going to have a remainder now of 12. Perfect. We're going to have a look at how we're going to convert this to letters again, yeah? Now, let's take the 50 across it and rinse and repeat. Divide 50 by 16 and change the mixed fraction. You should get 3 1/8. So take your time, guys, yeah? Take your time. And as usual, raise 8 to 16 by doubling. So double the fraction, you get 2 over 16, which is a remainder of 2 here. Lastly, put the 3 here. Now we're at the end, literally. Divided by 16, you're obviously going to get nothing. And a remainder of 3 over 16 because, well, there's nothing left except remainder 3. So the answer will be 3. And we're done, at least for this bit. So firstly, the 12, how is that written in? So how do we write this again? So the key idea is to firstly convert the number into the acceptable format. And just to recall, hexadecimal takes digits from 0, 1, 2, 3, all the way up to 9. And then after 9, instead of writing 10, we say A, B, C, D, E, and F, where each letter corresponds from 10, 11, 12, all the way up to 15. So F is the 15th. And all of this makes 16 digits for hexadecimal. And oh yeah, so 12 is going to be, let's see, 10, 11, 12. So 12 is C. And that means, as a hexadecimal number, we look upwards, so it'll be 3, 2, C. So that's the first half of the answer done. So it'll be 3, 2, C. Point. Now we need to find the decimal bit, the 0.25. And just like the binary one, well, you just multiply that by 16. So not bad, man, not bad. Just practice. So let's put 0.25 times that by 16. What do we get? You get 4. And you're done. Because you got the whole number, and this is one of the acceptable formats. Remember, it has to be within the acceptable formats to end there. And yeah, leave it there. Done. Okay, next one. So here we're going to learn how to express the hexadecimal number 8a.c in base 16 as a decimal number, which is the standard base 10 digits as usual, yeah? Now just to recall, hexadecimal numbers takes values from 0, 1, 2, all the way up to 9. And after 9 is going to be A, B, C, all the way up to, well, F. Okay, where each letter after corresponds to 10, 11, 12, 15, up to 15, yeah? So this makes total 16 digits. Now, what do we do? So just like the binary one, all you have to do is firstly rewrite this as 8a.c, and then because we're working with 16s, start from just after the before decimal and put this 16 to the power 0 here. This will give us the first representation, yeah? And then we continue increasing the power on the left side and then decreasing it on the right. And that's it. Now all you do here is literally find the sum product. And when you do that, you're going to get a perfect decimal number, which will give you what you want. So let's do that. So this means that the result is going to be 8 times 16 to the power 1 plus A, which is the same as 10. Remember, A here equals 10 and C here equals 12. So it'll be 10 times 16 to the power 0 plus C, which is 12 times 16 to the power negative 1. And that's it. You're done here. So all you do now is just smash down your calculator. Plus 12 times 16 power negative 1. And I got 138.75. See if you get the same thing, but this is the general idea. If you had more terms, I don't know, like 2, 7, then this will just increase. -2, -3, and so on. You just take the sum product of everything. That's all you do. Okay, guys, here we go. modular arithmetic. So in this case, we're going to learn how to add and subtract binary numbers. Yeah. So this is quite easy in my opinion. You just have to be very careful how you add. Yeah. It can be tricky too. I can't lie. Now, what do we need to take note of this? What's the difference between adding these numbers instead of regular base 10 numbers? Well, one thing we have to know is that when we use regular numbers, it always starts from 0 and goes up in 1. So 1, 2, 3, and so on. And eventually when it hits 9, it ends. When you get 10 or greater, we always seem to carry the 1 to the next digit. Now, it's kind of the same here. For binary, we only have 0s and 1. So what happens when you get a number bigger than 1? Well, you can think of it as the next digit, which is 10, or 0, 1, 0. After 10, you get 11. What happens after 11? Well, you carry the next one, it becomes 100. Then you get 101, and so on. But luckily, we'll only probably go as far as 11. Possibly. Actually, no, we'll probably go 10 at most, because 1 plus 1 will give you 10. Okay? Think of this as the second digit. So this is the second, third, and so on, yeah? So when you have two 1s, you make it 10. 1 plus 0 is 1. So let's just try this out, yeah? So first things first, I'm going to add these two first and then subtract the next one later. So let's write it down neatly. So 1, 1, 1, 0, 1 plus 1, 1, 1, 0, 1, 1. Okay, so start from the right hand side. So we're going to have 1 plus 1 will give us in binary 10. So it'll be 0, carry the 1. 1 plus nothing plus 1 gives us 10, carry the 1. 1 plus 1 plus 0 gives us 10, carry the 1. 1 plus 1 is 10, plus the extra 1 is 11, carry the 1. 1 plus 1 is 10, plus another 1 is 11. That's it. So you get 1, 1, 1, 0, 0, 0. Now, using this one, let's subtract the next one. So this has 5 digits, so 1, 1, 1, 1, 0. Okay, now we got to be very careful. So just like regular subtraction, you may need to borrow. You have to borrow from the next digit if the number is smaller than the one you're subtracting. So for example, 0 take away 0 is fine. Nothing take away nothing is nothing. Now 0 take away 1 you cannot do because it's smaller. So you need to borrow from his neighbor and you can't. So you borrow from the next one. So borrowing from this 1, you got nothing left. Give to him is 10. So cancelling 10 down, it's like the second. Now you have 1 left. Give him the 1. Cancel the 10, you're left with 1. Give him the extra 1. So now you got 10. Oops, actually, I think I went too far there. Oopsie. Yep, that's where we are. So 10 take away 1 gives us 1. So think of this one, the second take away the first gives us 1 left. Or think of this as 2 sets of 1s, 2 single 1s. Now 10 take away 1 is 1. Nothing take away 1 you can't do, so you borrow from here. Becomes a 10. 10 take away 1 is 1. You can't do, so borrow from here. Give him the 1. And you get 10 take away 1, which is 1. So this should be your final result. So it looks kind of similar. It's hard to tell like how big these values really are, but this is what you should get. It's always good to double check on Google and stuff. And anyways, but let me know what you guys get. If you get the same idea, excellent. But other than that, if you enjoyed it, leave me a like, subscribe, and please share it to your friends. And yeah, I'll see you next time. So here we need to find the smallest positive integer of mod 11 that is congruent. So congruent means identical to 2 of these digits. Now all this means is that we just have to work in mod 11. Okay, so literally mod 11. So this is a cycle. Now how do we do this? So the first term 58. So we can firstly say, what is 58 mod 11? The key idea, and this is a very handy trick for not digits that don't have massive powers, is to firstly you got 2 ways. First way is a cheap way. You keep subtracting 11 until you get a very small positive integer number that before it becomes negative basically. So in your calculator you could just write 58 take away 11, and doing that you get 47 mod 11. So it's just cycles 11, and then take away that answer by 11, and then you should have in your calculator answer minus 11, which is 36. And if you keep smashing the answer button, equal button, you'll eventually get to simply 3 mod 11, and that's the end. Alternatively, what we could have done, we could also do, you can use the remainder theorem, which is like the regular binary method. Just do 58 divided by 11, and then change as a mixed fraction. So 58, so you can put here 58 divided by 11 gives us exactly, goes into it 5 times with a remainder of 3. And all we care about is the cycle. So it has a third, after the 5th cycle, we have a remainder of 3. So the answer would be 3 mod 11. This is probably an easier way actually. So let's try that for 581 now. So 581 mod 11. So using the remainder theorem, you can just say 581 take away 11. That should give us, change it as a mixed fraction in your calculator, you should get 52 and 9/11ths, meaning the remainder is going to be 9 mod 11. And that's your answers for both. Okay, next one. So here we need to find the remainder on division by 11 of the following 3 types of sums and products and powers. So what this instantly means, you can use one or two methods. I always use the mod 11 method. Always use modular because it just makes life easy. And here you're just finding cycles of 11s. So let's have a look. So firstly, to make this life easy, what is 58 plus 581? Well, smash on the calculator and you should get exactly 613 mod 11. Now to find the remainder, use the remainder theorem and just divide this by 11. So we can say 639 by 11 and convert that to a mixed fraction. You should get 58 and 1/11. So technically the final result for this one would be 1 mod 11. Because we only care about the remainder. So it has a remainder of 1. As for question 2, same thing applies. So just smash 58 times 581 in the calculator. You should get a ridiculous sum of 33,698. And to find the remainder, divide that by 11 too. And convert that to a mixed fraction. You should get exactly 3,063 and 5/11. So it has a remainder of 5 mod 11. So a remainder of 5. Now the final one is also quite straightforward, but we need to use a very particular theorem. Now this theorem is quite beautiful actually, because it actually instantly solves this problem. So you might be familiar with this one, and the key idea is to take the base number a, and when you have a prime value like 11, which is perfect, we can say a to the power p mod that same prime value gives you itself a. And trust me, this is one of the most famous theorems in history. And we should thank a particular mathematician. Now, one of the cool things about this is that we can also do some indice rules. We can times both sides by a to the power negative 1. Because remember, this is a to the power 1. If you times it by a to negative 1, they cancel out and you're left with a whole 1. So times them both sides by that, you should get a to the p minus 1 mod p, and times a by a minus 1, you get just a whole 1. So this is another beautiful one. Now, why are we doing this, you're wondering? Well, look at the figure. You cannot smash this in your calculator. You're going to get a math error. You can do it on a computer, but you ain't going to bring a computer in the exam. So for those doing it manually, we need to use this theorem. So first things first, let's copy this in. So we got a is 581, and now using the second equation, because we want it equal to 1, because at least 1 is easier than equal to 581. We can say a to the power of the prime number, which is 11, minus 1 gives us 10 mod 11 is identical to 1. Now, how can we relate this to 20? Well, if you just times this by itself, that actually gives us, firstly, that's the same as 581 power 10 times 581 power 10. And we can, of course, add mod 11. Now, we both know that both of these, this equals 1. So this means literally 1 times 1. So 1 times 1 mod 11 is 1 mod 11. So the remainder is 1. Well, bravo. You know what? This was art. If you guys enjoyed this one, let me know. And really check this out. This is really cool method, and I can't stress how good it is. Welcome back, guys. So here we're going to try and figure out what is the additive and the multiplicative inverse of a certain number in terms of modulus. Now, first things first, what are we trying to find and what is it? So let's firstly work on the additive inverse. Now, The inverse property states that for adding is that we need to add a certain number to a term, say 5, and make sure it equals to 0. If there was no mod, we could say that in order to get 0, the certain number we could add is technically minus 5, because this guarantees a 0. This would be the so-called additive inverse. Okay? Now, in terms of mod, and this is the reason why I'm giving you a straight, easy example. 1, because it's an exam paper, and 2, because we don't need to necessarily find the mod of certain numbers. All we need to do is find how do we make 11 from 5? Literally, because when you have 11 mod 11, well, that gives you a 0. So to get that, we just add 6, and this will give us 11 mod 11, and that is 0 mod 11, and we're done. That's how you do the additive. The key idea is that a certain variable a plus b must give you 0 mod some term. Very straightforward. This is the additive inverse. Now, for the multiplicative inverse, not too bad. It's a bit different. The general property states that we need to have some term a, which we can take as 5, times some term, let's call it x, mod n, and this should give us eventually 1 mod n. Okay, so we need to somehow cancel each other out. So it's like saying, for example, 5 times 1 over 5 will give us 1. So the x value is technically the inverse of a. So to make it even more clear, technically, the correct term should technically be something like this. This is what we're actually looking for, a times the inverse of a. Now, the only way to do this, and now we're using prime, thankfully, is that we can use a very famous method known as Fermat's Little Theorem. And Fermat's Little Theorem was so profound that he got pretty much one of the most famous prizes known. So we can firstly define the formula. So Fermat's Little Theorem states that we have a term a to the power of some prime, mod that prime will give us that term back, a. Come on, this is art, guys, yeah? And now, what we could do to simplify this one, in order to make a 1 mod, you could just times both sides by a to the power negative 1. So that cancels the 1, and that simplifies to a to the p minus 1, mod p. And cancel a times a minus 1 is 1. Done. That's literally it. So now, what does this mean? So this actually tells us that to get 1, we can just simply find a negative 1. So actually, yeah, let's take this one step further. How to get a negative 1 from here? We can actually times, again, both sides by a negative 1. So we can have a to the power p minus 2, mod p. 1 times a negative 1 is a negative 1. And that's it, guys. This is the formula we want to use. So thank you, Fermat. You really helped us solve these kind of problems. So how do we get this? Let's have a go. Well, let's work with 5 mod 11, yeah? So we got the values here. So we can say firstly a is 5. Using the final formula, the prime value is 11. So it'll be 11 take away 2 is 9 mod 11. And this should equal, well, 5 to negative 1. Which is technically the value needed to times with the original value 5 to get a value 1. But we need to use a whole number. So let's work out this 5 power 9 mod 11 first. So let's work in the beginning. Let's work with 5 squared first, and let's try and make 5 to the power 9. 5 squared is 25. So this will give us 25 mod 11, which is the same as, and reducing this mod, remember you can just simply subtract it by 11 to get 14 and subtract 11 again, and you get left with 3. So quite straightforward. Always reduce it. So apparently 5 squared equals 3. That means 5 to the power 4, if you square both sides, will give you 9. That means 5 square again, 5 to the power 8 will give you 81. And 81 mod 11, again, do the same thing, keep subtracting 11. And eventually, when you keep subtracting 11 all the way, you should be left to 4. So finally, to get 5 to the power 9, we can just say 5 to the power 8 times 5 to the power 1 will give us literally 4 times 5. 5 to the power 1 is 5, so 4 times 5 is 20. And 20 mod 11 is going to be 9. Okay, part C now. So triangle ABC is an isosceles triangle which has 2 equal sides. That's what an isosceles triangle is. So one of the side is 6 centimeters and the other is 8. Find all possible values for the length of side C. So this question is asking us to find all different combinations. So first things first, let's just draw a regular isosceles triangle. Just any one will do. And we have to always indicate that two lengths like these ones are the same. Now suppose we had one length which is 6. This implies that the other length is automatically 6. And we also know that there's another length 8. So this is one combination. Now let's change the color of the pen. So let's find this one now. Yeah, let's find another one. So suppose now the long side had a length of 8. This means that this is also 8, meaning the other side is 6. And that's it. That's all you really do. Now for question 2, find all possible values for angle B. Well, I'm going to assume based on the triangle that we're going to have corner A, B, C. So angle B, not very clear, but this should be angle B. Okay, so let's call this one X. And the same for this one. I'm going to call this one here Y. So let's have a go and find all the values. Now, in order to do this, we need to use the cosine rule. Okay, so the cosine rule states this. So let me write this down. It states that the general formula is a squared must be equal to b squared plus c squared minus 2bc. Now, the cool times cos A. Now, the cool thing about this formula, that the cos A referring to is that there must be a single angle at point A. We don't necessarily need to call this B. We can reformulate this triangle and say the only angle here is X, so we can call this angle A with length A. Same thing here. We can call this one A with length A. So this means that X represents cos A would be cos X, and the one opposite the angle is a length A, which would be 8 squared. And that's it. Same with this one. This would be cos Y and 6 squared. And B and C would be the other two isosceles part. So we always need to find what the A's are. A's are the most important and BC's are the rest. So what I'm going to do now, because we need to find the valued angle, I'm going to go ahead and rearrange this to make cos A the subject. To do that, we can subtract, firstly, we can throw 2bc cos A on the other side, and then subtract a squared and divide by 2bc. So we should have something like this. So we can say cos A is equal to b squared plus c squared minus a squared over 2bc. You could do your own way and get a similar result, but it could most likely be backwards. But either way, it'll be fine. So now all we do is smash the values in. So we can say first triangle, let's call this, so the good thing I called it X and Y. So we can say for the one that has cos X, the first one, we can say b squared plus c squared. So this would be b and c. So this means 6 squared plus 6 squared minus 8 squared over 2 times 6 times 6 would equal something, whereas cos Y would be the other one. So this would be, the b and c would be 8 here. So this would be 8 squared plus 8 squared minus 6 squared over 2 times 8 times 8 would also equal something. So let's go ahead and evaluate both now, yeah? So take your time, guys. So 6 squared plus 6 squared minus 8 squared over 2 times 6 times 6. So the first one I got 1 over 9. So cos X is, where's my pen? 1 over 9. So this means if you found the inverse, so remember to find the angle you need to find inverse. So the inverse of this one. Now I'm going to keep the answers in degrees just so it doesn't look confusing in radians. So in degrees, the cos inverse of this will give me, okay, I got 83.6 degrees. I mean, you guys could have got something similar, but let's see if you got that. Whereas for the second term, now let's expand, let's solve 8 squared. So 8 squared plus 8 squared minus 6 squared over 2 times 8 times 8. Second one I got 23 over 32. And finding the cos inverse of that, so shift cos inverse, and I got 44 degrees. So y equals 44.0 degrees. Okay, here we go. Now, let fx equal this typical representation of cos and this representation of sine. So we got cos x plus pi and 2 sine x. Now what does this mean? So firstly, this sine x has been stretched upwards and downwards by 2. So this is a stretch on the y-axis. So we have to draw the gx function first, which is probably easy to do first. So here's a regular, let's just draw a regular sine. It looks a bit like this, right? And on this side too. This is the sine wave where you got a maximum height of 1 and the minimum height of -1. So now this graph, 2 sine x means it's going to be a stretch on y-axis. So this is now going to stretch right to the top here and go back down, stretch right to the bottom here. That's a curving actually, and then go back here. So it stretches all the way to -2 and all the way up to +2. As for the cos x plus pi, and oh yeah, it does the same on the left side. As for the cos x plus pi, that's just a shift in the x-axis. So if it's plus pi, it means shifts to the left. So this is a left shift by direction of pi. Just to reference it, the sine graph. The sine graphs here, and these are the following points here. At this point, intersects at pi, and this is 2 pi. These points here are basically pi over 2, so half of pi, and these points here is 3 pi over 2, so 1.5 pi. So halfway between pi and 2 pi. And the same could be said for the negative values. As for the cos x plus pi, let's just draw it out here, yeah? Always good to have it out. So the regular cos x graph will look a bit like this, yeah? So let me just extend the line. So here's the blue line. There you go. So this tells us that at this point, this is pi over 2, this is pi, this is 3 pi. That's quite poorly done. So this is 3 pi over 2, and this one here represents 2 pi. Okay, so this is pi here. So if you're going to shift this to the left now, following this example here, what exactly happens? Well, I'm going to change the color pen. All this means is that this entire graph, so this point is going to hit here, this is going to hit further down. So let's have a go. So if this shifts here, this is going to be here, this is going to be here now. Negative, this would be a negative pi over 2. 3 pi over 2 is going to be here, and this one's going to be here. So it's going to look a bit like this now. So it's just a shift, and it curls back up here, all the way to minus pi. And that's it. So does this mean anything for these questions? No, not really. All it means now for the amplitude, frequency, and period, or at least for cos, is that it doesn't change. How do we know? So what is amplitude? The amplitude is defined as the following. According to the CGP book, the amplitude is the height of the wave, literally this little gap here. So going back in our diagram, it's just going to be literally this part here, or I don't know, this part here even. And we know that they both have 1. According to the sine wave, because it's 2 sine wave, it's a really long amplitude. So the amplitude for the sine wave, that's right here, equals 2. Whilst for the cos graph, the amplitude here is going to be 1. It's just a standard 1. Now, how about the frequency and the period? Well, the frequency is simply how many complete waves we have per second. So if we start from here, we can see it completes all the way here. So this is known as a complete wave from when you do a full circle. Now, going back to our graphs, we can say that if we start from, let's say, this point here, from 0, if we follow this line right to the top, it does a complete wave of 2 pi. So technically the frequency is 2 pi. And it's also the same for the sine. It also starts from 0, ends at 2 pi. So this is also 2 pi. So frequency here is 2 pi. So nothing really changes. The period is simply the same thing as the frequency, but it's now 1 over the frequency. So the period is 1 over the frequency, which is 1 over 2 pi. And likewise here, this would also be the same one. Okay, finally. Now, by plotting the graphs of fx and gx, or otherwise, find all the values of x between minus pi and pi. Now, you could technically just plot the graph and just have a careful look, but I will take the otherwise option because there is actually a much more easier way to solve this problem. And I can show you how. But it requires the use of something known as the double angle formula, or the sum and subtraction of the cosines inside. So let's have a look. So what is this representation below saying? So we need to solve between minus pi and pi, for which cos x plus pi minus this is 0. So it's just saying, you know, pretty much subtract these two and solve it, or equate these two and solve it. So let's work out what cos x plus pi is, yeah? So cos x plus pi, there is a beautiful expansion known as cos a plus b. And this tells us that if you expand this, you'll get cos A and cos B. Instead of plus, it would be minus sine A and sine B. There is a proof to this, so it's good to look online. If you were subtracting, then in the end you'll be adding. But in this case, we're just going to be adding, so we're going to use the subtraction term. Okay. Now let's repeat what we just did for x plus pi. Yeah. So expanding that, we're going to have therefore cos x and cos pi minus sine x and sine pi. Now, why is this useful? Well, we can instantly look at this and realize that sine pi and cos pi are actual values. So make sure your calculator is in radian mode. Yeah, that's the most important thing. And just smash sine pi in your calculator, and you'll realize that this would equal 0. So actually, all of this cancels out because sine x times 0 is 0. Now you're left with cos x and cos pi. Now, what is cos pi? That's the question. Well, cos pi is actually minus 1. So all of this will be minus 1 times cos x is minus cos x. And that's it. All of cos x plus pi is identical to minus cos x. That's it. So that's perfect. So now if we rewrite this entire equation with our new result, we can say that minus cos x minus 2 sine x is 0. Now the cool thing about this is that you need to realize that you could, if you literally just make one of these subjects, you can rewrite this as a form of tan x, which is great. So let's do this. So let me think. So let's firstly divide, well, there's many ways. Let's divide everything by cos x, yeah? If you do that, this becomes minus 1, and then this part becomes, so you can have sine x over cos x, and that's going to become tan x. One of the properties here is that sine x over cos x is equal to tan x. So that's what we're trying to observe. So that's one way to eliminate these terms. When you have terms in terms of sine and cos, always try and rewrite them in tan. Another way you could do this is make cos x subject, divide cos, and then you'll get sine over cos. Either way works fine. And then 0 divided by cos is still 0. Now let's make 2 tan x the subject. So add 1 across. So we'll have minus 2 tan x equals 1. And then divide minus 2. You're going to have tan x equals minus half. Easy. Now this one is great. So this minus half, what could we do with it? Well, we can always input up here minus half. We could always find a tan inverse. So let's find a tan inverse of minus half. And you should get in radian mode, well, it doesn't really tell you. Oh yeah, in radian mode, because we're solving radian mode, you'll get a value of minus 0.46 radians. Now, the only way to solve this is to use something known as the CAST diagram. That is CAST. Typically, when you're solving terms of tan, we'll use T and we'll use A. A means you always use all. Now it depends on the result. If the result was positive for tan, so this is specifically for tan x, yeah? If the result was positive, we would use A and T. Now given that the result was negative, like tan x was negative, we're going to use S and C, the negative terms. Because these, if you're using tan, the sine and cos part are excluded since they're negative. So let's plot this. So minus 0.646 would be here and here then. And now all we do is just measure the angle. So we start from the 0 line. So this is the 0 line, and we just draw one arrow here. This is a total of pi, by the way. So to make it absolutely clear, to find all solutions, well, we start from the 0 line and we just draw an arrow which hits this. So this means that we're an angle of this quantity. And to find this angle, we know that angles on a straight line add up to 180 or pi. So since this is 0.46, this would be pi minus 0.46. So this is the other angle. Minus 0.46, and the other angle is up to this line, but we know this line. This angle has an angle of 0.46, but because we're going downwards, it would be minus 0.46, and we've already got it here. So this and your other solution would be pi minus 0.46, and that is equal to, so pi minus 0.46. That should give you minus, wait. Hold on, pi, you should get 2.68, yep, that looks about right, and radians, and that's it, we're done. So this should be your final result. You could do it graphically, but I think this is enough. But anyway guys, hope this helps, and let me know how you do, And other than that, I shall see you next time. Ciao.